So what we're starting today is our unit on statistics and probabilities. Okay, now probability is basically trying to figure out what your chances are or how likely something is to happen. Okay, probabilities are used all the time. Even athletic teams will hire a director of analytics. And basically, they're studying the numbers, they're studying the probabilities, the statistics of their players, and they're trying to come up with the best strategies to help their teams win. Baseball season just started, and you'll see, especially late in the game, they might switch pitchers multiple times really quickly. And it's not because they're tired, but it's because statistically, the person who's coming up to bat doesn't do as well against a right-handed pitcher as he does against a left-handed pitcher. So they switch to a right-handed pitcher because based on the probabilities, they think they have a better chance of getting that batter out. So there's a lot of, that's a kind of a simplistic example, but there's a lot of different areas where these probabilities are used. So we're going to start, first of all, by learning how to calculate how many of something there is. Okay? Basically, we're just going to learn how to count in this first couple lessons. All right? And the idea is, in order to understand how likely something is to happen, we have to be able to figure out how many ways it could happen. And also, we have to be able to figure out how many ways how many different outcomes are possible. Not just the ones we want, but how many outcomes are possible in a particular situation. All right, so all of that has to do with counting. Now, one thing I want to look at first of all is a couple of the tools that are used commonly in probability problems. And this is partly because we have a lot where English isn't your first language, but also, even if it is, just making sure you guys understand the terms involved here that are related to some of the situations you'll be given. And also, so that you guys understand, a lot of the applications that we're doing here might seem silly or why would we even bother trying to figure that out? But understand that we're learning the foundational principles here. And the reason why we use sometimes silly examples or whatnot is because to actually look at a real life example, it would get way too complex for our level right now. So we're learning the principles behind it, and then if you go on to study higher level statistics or probabilities later, you can get into analyzing all the different variables and all the different possibilities that could happen in a given situation. And that's where you have whole careers that are built on that. Okay? You have, oh, now I just blanked on the name of it. Actuarial science. Okay? Actuarial science is a study of probability and statistics that is used by insurance companies to analyze risk. Okay? And that's how they set your insurance rates for driving or for, for your house, your property, that sort of thing. Okay? House insurance down here is a lot higher than it is up in Ohio, where I'm from. Okay? Why? Because while we have a lot of snow in Ohio, we don't have hurricanes. Okay? Here, a hurricane could come through and just level everything. Up north in Ohio, we don't even really have tornadoes that often. In our area, actually, we haven't had a tornado my entire life where we were at. So the probability is that they're going to have much less of a chance to have to replace my house if I live up there than if we live down here. Okay? Or cars. Auto insurance down here is a whole lot more expensive than it is up there. Why? Because that was a more suburban area. or even rural areas in parts. Here, I don't know if you realize, but Broward County and Miami-Dade County has one of the highest population densities in the country, which means there are a whole lot of people in a really small space. And add to that the amount of senior citizens who are driving and the amount of people who don't have licenses who are driving illegally around here, all of that increases the risk of getting in an accident. So an actuary is going to look at all those probabilities and look at the statistics of the environment, and they're going to say, okay, we need to charge this much to insure you. Okay? That's also why high school guys have higher insurance than even high school girls. High school guys tend to be a little more immature and reckless than high school girls do. However, once you hit like age 25, that actually goes down. Because I guess 25 is their magic number according to their statistics. So one guy's kind of grow up and quit doing stupid things. But that's debatable. If you get married, your insurance rates usually go down because you have someone there who's you need to be there for. So it usually tends to make you do fewer stupid things in life. So there's a lot of different stuff that they take into account, and you can see how all the different variables are now coming into play. Where you live, who you are, what age you are you married, do you have kids, what's your driving history, okay? All of that comes into play in just that one number. And that's just one example of thousands in life where probability and statistics is used. So, we're going to keep it simple though. And we're going to learn the basic principles behind it. So let's look at the couple of tools. First of all, coins, heads or tails. Okay, there's a head. We have George Washington on our quarter, and we can flip that coin, and eventually, there we go, we've got a tails. Okay, heads and tails are the two sides of the coin. Dice, all right, you're familiar with rolling dice in a game or something. Okay, if you have more than one, they're called dice. If you have one, it's called a die. All right. And typically dice have the numbers 1 through 6 on them. Although it's possible that you could have dice with more than 6 sides. At one point I had a 20-sided die. That was interesting. So it's kind of a cool shape. It was an icosahedron. So that's a 20-sided 3D object. And then the last one is a standard deck of cards. This one's nice because it actually has a lot of different variables in a deck of cards that we can consider. All right, but especially if you're not familiar with a deck of cards, or even if you're just not familiar with the terms related to a deck of cards, it's helpful to understand. First of all, a standard deck of cards is going to have 52 cards. All right, no jokers. Just 52 cards. We have 2 colors, red and black. So each color, there are, how many of them? 26 of each color. All right. There are 4 suits. Okay. And since there's 4 suits, there's 13 in each suit. Okay. And 2 of the suits, hearts and diamonds. Okay, here's a diamond, and here's a heart. Okay, hearts and diamonds are both red. And then you have spades and clubs. Okay, spades and clubs are both black. Okay, and then each suit has ace, which is a 1.
Or 11.
Okay, if you're playing blackjack, it could be 11. But aces are 1, and then 2 through 10, the numbers, and then you have a jack, queen, and king. Okay, The Jack, Queen, and King are known as the face cards, and that's because, if you look down here, alright, they have people on them, okay? So, and some of them have some funny names, like the king with the sword in his head is the Suicide King. Yeah, I don't know why they made him with a sword going into his head, but any of the one-eyed jacks are the ones where you can only see half their face. Anyways, kind of interesting. Every deck is a little different. But here you have the different suits. Here's the black clubs, the red hearts, the red diamonds, and the black spades. And anyways, each suit then has 3 face cards, so there are a total of 12 face cards in a deck. Okay? So, I just wanted to make sure that you guys understand, especially if you've never played cards or you're not familiar with some of these terms, make sure you write this stuff down, and so that when you're presented with a problem, you know what you're dealing with. Okay? Alright, so let's talk about some counting principles and some things to consider particularly. We're really delving into a branch of mathematics called combinatorics. There's an entire study of this. If you go to college, and you can take a combinatorics class if you want. Basically, it's a whole class on how to count things. Alright? But combinatorics, we have 2 questions we need to consider when we're trying to figure out how many ways something can happen. Alright? First of all, does the order of the items that we're selecting matter? Okay? In other words, are we voting for a president, vice president, secretary, or are we voting for a 3-person committee? Okay? Because in the one, there are unique spots that need to be filled, but in the other, it's just 3 people on a committee, and it doesn't matter. There are no positions within there. Okay? So in that case, order wouldn't matter. Are we looking for the finishers in a race, first, second, or third? Or are we just looking for our top 3 runners? Okay? So, there are 2 terms here that you really need to make sure you understand. The first of these is permutations. Okay? A permutation is an arrangement of items in order. Okay? It's an arrangement of items in order. Permutation. The second one we've looked at already in the past, and that is a combination. Okay? A combination. A combination is simply a collection of items in a group. Okay? So, permutation, the order matters. Combination, the order doesn't matter. Okay? So think about your situation. Am I selecting a group of things? Like, if I'm playing cards, and I'm dealt 5 cards, or 6 cards, okay? I'm dealt a group of cards. It doesn't matter what order they're in, because I could just rearrange them if I want, okay? However, in a different circumstance, the order might matter. All right. What is this called?
Combination lock.
A combination lock.
It's a permutation lock.
They have an entire industry that's named incorrectly. Okay? Because these aren't combination locks. These are actually permutation locks. Because while the numbers 12, 30, and 0 will unlock this, it'll only unlock it if I put those 3 numbers in the correct order. Okay? So the order matters. So, kind of interesting. They named it wrong in the first place, but it's stuck. It's easier to say probably too. But anyways, permutations and combinations. First question you need to ask, does the order matter? Secondly, another thing to consider is, are the items that I'm picking being replaced each time one is chosen? Okay, now think with me here. Let's say I'm picking out a card. What are my chances in a 52 card deck that I pick the Ace of Hearts?
152.
1 in 52.
Hard,
Okay? Oh, I didn't get it. Alright? So what are my chances of picking out the Ace of Hearts now? 1 in 51, unless I stick this card back in, right? If I've replaced it, then my probability stays 1 out of 52. If I take it out, and I keep it out, then the next time it's 1 out of 51. And then 1 out of 50. And then 1 out of 49. Okay? So if you had 10 people picking out, trying to get the Ace of Hearts, and everyone was going to keep their card, okay, then as people continued to pull one out and not get it, your chances would actually be better. Okay? And we could keep picking here for a long time and not get it. So you have to consider your situation. Are they being replaced each time we're choosing one? Okay? In other words, can it repeat? Alright, I pick an 8 of clubs. Could I get an 8 of clubs the next time? Or is it gone now? So we have two terms that are somewhat related to this. They are not opposites. Okay, don't think that these two terms are opposites of each other. They're just two terms related to this concept. One is independent. Okay? One is independent. One event happening has no impact on how the next event will happen. Okay? So, if I pick a card out and I don't get the Ace of Hearts, if I keep that card out, then that impacts the next one, right? So that would not be independent events. But if I put that card back in, then it doesn't matter what I picked the first time. Even if I pick the Ace of Hearts the first time, if I stick it back in the deck, that's not going to impact what I could get the next time. Alright? If I roll a die, and I roll a 1, and then I pick that die up and I roll it again, I could still get a 1. Okay? The chances won't change. Now, another concept that's somewhat related here, but I want to make sure that you get the term down, is mutually exclusive events. And here we're talking about two events that cannot happen at the same time. Okay? So let's think about rolling a die. Okay? Rolling a die. Okay? Let's say one of my events is rolling an even number. What is something that's impossible to do if I roll an even number? Roll an odd number. Okay? I'm only rolling one number, and there are no numbers out there that are both even and odd. Okay? So those would be mutually exclusive events. What's another thing? I could roll an even number, or roll... Huh?
You can get an odd number. There's a die sold in Target that has 1, 3, 4 on one side.
What?
There is a kind of dice sold in Target, and there are three numbers on one side.
3 numbers on one side.
Yeah.
Okay? We couldn't roll an even number and a 5 at the same time. Okay? Or how about could I roll an even number and a prime number? Can I?
Yeah.
Yeah, 2, right? So, are even and prime mutually exclusive? No. All right? These would not be mutually exclusive because it's possible for both of those to happen at the same time. Okay? So, those are some of the basic terms related to things we're going to look at here in probability. But we've got to make sure we understand them so we can count things right and so we can calculate probabilities correctly as well. All right? So let's talk about our fundamental counting principle. I'm going to show you what the book gives us, and then we'll try to put this in our own words. Okay? So here's what we have. E1 and E2 are 2 events. Okay? 2 events. The first event, E1, can occur in M1 different ways. And then after E1 has occurred, E2 can occur in M2 different ways. The number of ways that the 2 events can occur is M1 times M2. Alright, now, you might get that, you might not. That's okay, but let's think this through, and let's use an example, actually, to help us understand what this is talking about. Okay? So suppose you pick 2 cards from a deck, and you replace the first card before you draw the second one. Alright, so we are replacing. How many ways could you pick a diamond the first time and a face card the second time?
What is diamond?
Okay? A diamond is one of our suits. Alright? And if you don't, that's okay if you don't understand that. You were out of the room when we did that. So we had the 4 suits. These are our diamonds. Okay? So let's think this through here. Okay? What are the 2 events?
Diamond and face card?
Yeah, picking a diamond, we'll call that E1, and picking a face card. That'll be our E2. Okay? So, M1 is how many different ways could we get a diamond?
13.
13. There's 13 diamonds in the deck. Okay? How many different ways could we get a face card?
12.
12. There's 3 in each suit times 4 suits. Okay? So 12. So, according to our fundamental counting principle, alright, the total number of ways that we could get a diamond and a face card would be 13 times 12. 156 ways. Okay? Alright, does that make sense? Okay? So, let's see why this works. Alright? Why does this work? Well, here's our diamond. We said we had 13 of those, right? So here's our 13 diamonds. 4, 5, 6, 7, 8, 9, 10. 4, 13. 3. Yeah, 13. Okay. And then let's come up with our face cards. So here's a king. Here's a queen. Here's a jack. Oh, cards are usually rectangular. Here we go.
Usually. Not always.
Here's our jack. It depends on if your little brother or sister got a hold of it. Alright. So there's 3 of them. There's 3 more. There's 3 more. Okay. And there's 3 more. Alright, so we've got all of our face cards here. Okay? Now the reason why this works is because for every one of these diamonds, okay, we'll use this one. Every one of these diamonds, I could I could have picked this diamond and the king, or this diamond and this jack, or this queen, or this king, or this king, or this jack, or this queen, or that queen, or that jack, or that king, or that jack, or that queen. Alright, so I had 13 different possibilities just from that one. And then, 12 possibilities just from that one. And the rest of these all have the same 12 possibilities. Okay, that's where this principle comes from. These 13 each have 12 possibilities. So 13 times 12 is the total number of ways.
I'm assuming you're talking about card. So what if one of like the diamonds was a base card diamond?
Well, that's what we said. You just came in, okay?
Oh,
We
sorry.
said we replaced the first card before we picked the second card out.
Oh, sorry.
So that'll
My bad.
take care of it. That's okay. That'll take care of that. Now, we can look at that probability of what if we don't put the card back and we didn't pick a face card, or we did pick a face card and we're looking at probabilities. When we're doing probabilities, we would consider that kind of thing, and it would impact our probability. We would use something called Bayes' theorem, where we would look at conditional probabilities. But anyways, right now we're just counting how many ways something could happen. Alright, and in this case we've got 156 ways. Alright, so that's our fundamental counting principle. One other way we can count is counting things as they're arranged in order. And we mentioned the word permutation earlier. Okay? Permutations. Some notation here. N permutation R, NPR. The N and R would be subscripts. Okay, so they're written small before and after the P. We're going to arrange R items out of a total of N. And we're going to arrange them in a specific order. So we care about the order here. So let's talk about this first of all. Let's say that we have N items, and we want to arrange all of them. Okay? In this case, we have 6 letters of the alphabet, A, B, C, D, E, and F. We want to arrange them all in order. So 1, 2, 3, 4, 5, 6. There's 6 slots that we need to fill. 1 with each letter. You need to think of this in terms of being 6 events, so to speak. We're placing the first one, we're placing the second one, placing the third one, and so on. Okay? So how many options do we have for this first one?
6.
6. Okay? Now, do we want to use any of these letters twice?
No.
No, we just want to arrange those 6 in an order. So after we place the first one, how many options do we have for the second? 5. And then, okay?
So 720.
Yeah, good. That's 720 because those are all different events, and using our fundamental counting principle, we would just multiply all those together. Okay? Now, just for a little extra part here, before we move on, what if I wanted to proceed this with a number from 0 to 9?
Maybe 7. Oh, no.
How many options would that have?
10.
10. So, that'd be 7,200.
Yeah.
Notice how just adding 1 digit can really make the number a lot higher. Okay?
It's like
When I was
C.
little, all the license plates in Ohio had 3 letters and 3 numbers. And then at some point when I was in about middle school, they started putting 4 numbers on them because they were running out. But just adding that 1 extra number gave them, tons and tons of new options. Okay? So, anyways, let's go back to the original example we were looking at. What's another way that I could write that?
C.
Okay.
6.
Which is,
6.
6. No.
what's the exclamation called?
Factorial.
Factorial.
Yeah,
Okay.
yeah, factorial.
Yeah. All right. So 6 factorial. We're going to be dealing with factorials again. We're going to have them a lot. Okay.
Yeah.
So that's another way we could express it, and this is actually a rule for permutations. Okay. When we're finding the number of permutations for all the elements that are available, we have 6 factorial. Okay? So, for example, there's 21 of you here. If we went out and all ran a race, assuming all of you have equal running ability, how many different ways could we end that race? From the first person to the last person.
A whole bunch.
21
A bunch.
times 19 times
21 times 20 times 19 times 18, so what is that?
21 factorial.
21 factorial, okay?
Oh.
21, that's all I was looking for, not a
I was like,
number.
oh.
5.1 times 10 to the 13.
Yeah, a lot of different ways, okay? So we have, 21 factorial if all of you ran the race and all of you had an equal ability to potentially win or come in last, alright? So, and that's true no matter what you're dealing with. If you're ordering all of the items available, it's just going to be how many are there factorial, okay? So, have a very easy way to calculate some big numbers, okay? So, what if we don't really care about anyone who finished below third, okay? Well, we can eliminate those. Let's do it with a little smaller number. Let's say we've got 8 horses running in a race, okay? How many different ways can they come in first, second, and third?
C.
Alright,
C.
so notice instead of 6 events, we only have 3 events. And we don't care what happened to the 4th through 8th place. Alright? So, how many possibilities could we come up with for first place? 8. And then how many for second place?
7.
7. And third place?
6.
6. So 8 times 7 times 6 gives us 336 different possible outcomes just for first, second, or third place. Okay? So if you're ever thinking of going to the racetrack and betting on the trifecta, don't bother. You have less than 1/3% chance of actually getting it right.
What?
C5.
Yes. Okay?
C5 factorial.
There's a reason why places that host gambling have lots of really nice, expensive stuff, and it's not because everybody's winning. Alright? So, do the math and don't waste your time. Anyways, moving on. How can we write this in a simpler way? Okay?
C. Is that C?
This is where the permutation comes into play. And we'll look at an actual formula for the permutation. Alright? What we just did here is we had 8 horses to choose from, and we wanted to put 3 of them in order. Okay? You'll see the notation here, and I'll write it bigger so you can read it a little better. NPR, N permutation R. And what that means is we have N items to choose from, and we're picking 3 of them and arranging them.
Did we by chance do this in the beginning of the year?
We did combinations,
Okay. Okay.
which is a similar formula, but not exactly the same. So we're doing N factorial over N minus R factorial. So let's look back at our problem again, and in this one, doing it the way we did is the most efficient. But, just to see the formula here, if I have 21 or I'm sorry, if I have 8 horses and I'm arranging 3 of them in order, okay, 8 factorial would give me the arrangement of all of them, okay, but I'm going to divide this to get rid of the ones I don't want, okay. I have 8 minus 3, okay, so this is 8 factorial over 5 factorial. Now think, in the race, which finishers did we care about? First, second, and third. So how many places did we not care about? 5 of them. We didn't care about the other 5. So here we're getting rid of these 5.
So
This is all the arrangements of 5th through 8th place, basically. Okay? So, or 4th through 8th. So there we have that, and that does come out, if you remember how to simplify, 8 times 7 times 6 times, the rest of it would be 5 factorial over 5 factorial, and then you can reduce that, and that is 336. Okay? So you say, well, why do we use the formula? Why don't we just come up with that? Well, if we had, 500 things, and we wanted to find the order of the first 100 of them, that would get really tedious. That's where our formulas really help.
Hello, everyone. Please pardon this announcement. I want to remind all 9th grade
Oh my god.
graders to go to Lakeside and vote. Teachers, please ensure that if you teach 9th graders, they are dismissed to Lakeside to vote. 7th period, we will allow 8th graders to vote for their runoff. But at this time, all 9th graders must have voted at Lakeside. Thank you.
And then
Bye.
All right.
This is like binomial theorem, like what we talked about.
When we did the binomial theorem, we used combinations to get our coefficients. Okay? There was an extra part of the combination, if you remember, was this, but it also had an r factorial on the bottom.
right.
Okay? Yes.
If it was asking for all 8 places, would you just put like a 1 in the bottom?
If it was asking for what?
Like if you wanted to know how many combinations of all 8 places, all 8 horses.
All 8
Instead
horses?
of just percentage.
Well, think about it. We would be doing 8 permutation 8. So you'd have 8 factorial over 8 minus 8.
Which is 0.
0 factorial. Do you remember what 0 factorial equals? 1. Okay. No, that's good thinking. I mean that's the kind of those are the kinds of connections I want you guys to make here. All right. So, any other questions about our fundamental counting principle and about our permutations? All right. Now, I gave you guys some different problems. Try to think through each one of these. Write them out, okay? If there's a word you don't understand, look it up, okay? Or ask someone. But here we have 9 through 12, 17 and 18. All right, couple other problems. Here I only had listed 23, 25, 27. Anyways. And then 33, 34, 35. Okay. And 36, 37, 38, 39, 40. There's a lot of these. Once you get the hang of them, though, they should go relatively quickly, okay? I want you guys to make sure that you are getting the idea here at the beginning, okay? All right. And that's